Okay, it's Earth Science time we're doing today. We're going to talk about, well, let's just call it geologic time, and we'll see how far we can get in this. We might have to have another discussion before we take the test, but maybe not. So we'll call this geologic time. This will be a very, very brief rundown. The first two things we're going to talk about are relative, and this should be review. It is review, but we should talk about it again. Relative and absolute dating. Dating meaning not well, you're more or less adult. So when you drive your own car to Arby's with your girlfriend and buy her an Arby's sandwich, not that kind of dating. This is dating where we're trying to discover the dates of various geological or biological things. We have two kinds, relative and absolute. What is probably the difference here? This is the same way we use relative and absolute, for instance, when we're talking about spreadsheets or when we're talking about any other kind of reference. What is the difference? What do those words mean, relative and absolute? They're both adjectives. What do they mean?
Relative is like kind of close to, but
Yeah,
might not be the exact.
you mean, if you say like, I'm relatively certain
Yeah.
that it's going to snow today. Relative there means, as it does in all things, that you're making a comparison. Compared to how you might know that it's going to snow, you have a relative certainty compared to how you usually do. Tristan is relatively tall. Relative to what? Relativity is a major thing in all kinds of science. Relative to what is Tristan tall? Is Tristan tall relative to the Eiffel Tower? No. Tristan is not. He is relatively tall, we say, meaning relative to any other thing, yeah, other people, maybe you other three people. So we're making a comparison when we do relative. Whereas absolute, if I said Tristan's absolute height, that does not mean, it doesn't mean, and a lot of people have a confusion about this, it doesn't mean we're approximately sure of it in relative and we're definitely sure of it in absolute. That is not what it means. This does not mean almost, and this does not mean definite. Those are misconceptions. But in this one, it does mean that we're making a comparison. And in this one, we're telling actual numerical. So what is Tristan's relative height? Give me an example of Tristan's relative height. God bless you. No, that's not relative. Example of Tristan's relative height.
He is a student's relative.
Yeah, he's tall compared to Marissa is a relative height. Let's use that as an example. Tall compared to Marissa. Give me Tristan's absolute height.
Tristan is 5'9".
He's not. He's certainly more than that, but we'll say he's 1.8 meters. That's probably, oops, not parenthesis, quote. This is an example. 1.8 meters it's numerical. It's an absolute number. So now when we talk about this in terms of dating, these are examples with Tristan. When we talk about these in terms of dating, how will that apply? If we're talking about the relative or absolute ages of, for instance, a fossil, what would be an example of a relative age of a fossil?
It is older than a.
Yeah, geology. We would say something like the fossil is older than the layer it is found. Oops, not, doesn't have an M in it. Found in. It must be. If the fossil is found in a layer of sedimentary rock, that sediment, the fossil itself must have existed before that layer did, otherwise how did it get in there? Older than the layer it is found in, and absolute age dating, we might say it is 68 million years old. Let's have a little side note over here. Tell me these abbreviations again. This should be review. Abbreviations for ages. Yeah, so let's start from the top. Capital G, capital A is giga onum, and that means a billion years. Next one. Mega onum, which means a million years. And the last one we commonly use is kilo or kilo onum, which is 1,000 years. You need to have those memorized. Okay, so this is the basic information. We know what relative age dating is, and we know what absolute age dating is, but now we're going to talk about how we do those two things. So I'm going to erase this top part where we have the general information, and we're going to talk about how we do each of these things. We're going to keep the boxes here. We're going to talk about how we do each of these things in geology. Let's start with relative age dating. The ideas for relative age dating are from a man called Nicholas Steno, who I think was Danish. Dutch, maybe? I don't know. Steno's principles is what we call them. Steno's principles. They're sometimes just called the principles of relative age dating, but Steno's principles after Nicholas Steno, who, I don't know if I would say developed, but he first postulated them. The first one is the easiest, the law of superposition. You remember this one. What is it? What's the law of superposition? We've talked about this before. The law of superposition is that, well, if we have a pile of lumber, where are the logs that were first in the pile of lumber? Where in the pile are the first logs that we put in the pile? The bottom. If we have a pile of laundry in our room, where's the oldest clothes in the pile of laundry? The bottom. Can things happen to the log pile or the clothes pile that make it so that's not true? Yeah. But generally, if everything else has been normal, those two things are true. If we have a pizza, what did we have to put down first to make the pizza in the right order? The crust. The crust has to go first because it's on the bottom. We want it on the bottom, so we put it down first. That's the law of superposition. The oldest rocks are on the bottom. Always true? No. Just like the pile of laundry, right? Your little brother can come in and flip over the pile of laundry. In relation to the rocks, what could flip over the rocks? Little brothers? No. What? What force on earth can flip over the rocks? Probably not. Neither of those. No? No. What could cause a whole formation of rocks to be overturned, to be flipped over? Or even not necessarily all the way over, but like go like that, or move. What force on earth could move whole areas of rock? Plate tectonics. Plate tectonics. So sometimes tectonic plates or plate tectonics do cause this to be false, but there's usually other evidence that is the case. For instance, if we see layers of rocks that look like this, which we sometimes do, but fairly rarely, and they're folded like that, we know that something must have happened. Okay, so the law of superposition. 2, and these are not necessarily in order, I'm just going to put them out as I remember them, cross-cutting features. In the same way, if I have a layer of rocks here, and there's a fault that goes across it, what must be true of the fault relative to the layers of rock? The fault must be in age. We're talking about relative dating. In age, what must be true of the fault compared to the rocks? The fault must be younger than the rocks. There can't be a fault in rocks if the rocks don't exist yet. And so if we see this kind of thing, where there's a fault through these layers of rocks, but not this one, we know the fault happened. Let's say we had first A, then B, then C, then D, then E. Then the fault would be F, which kind of lined up nicely. And then this layer must be G. It's newer than the fault because the fault doesn't go through it. Cross-cutting features. Things that cut across. A fault, a dike, like an igneous intrusion. Those things must be newer than the things they cut across. So features are more recent than the rock they cut across. Next one we could say original horizontality and lateral continuity. These are kind of big words, especially for a adolescent, which you guys are. What might original horizontality refer to? What's horizontality? Being horizontal, the state of being horizontal. So if we're talking about original horizontality, we're talking that when excuse me, that when sediments are laid down, they're originally horizontal. They're laid down in horizontal lines. Once again, always true? No, but because of gravity, almost always, when sediments are laid down, they're laid down horizontally. And likewise, when they're laid down, what does lateral continuity mean? If horizontality is the state of being horizontal, continuity is probably the state of being horizontality is about being horizontal. Continuity is about being, no? Continuous. So the layers were not only originally horizontal, even if they're not horizontal anymore, they were originally, but they're also continuous. So if we see there's a valley through some sediments, this is still the same sediment layer as that. It's just that this valley has formed between them. They were originally horizontal, and they were originally continuous. So features or rock formations are laid down. You know what I mean by laid down? They are, what's the other verb we could use for that? When sediments they stop being eroded, yeah, they're deposited. So we could either say laid down or deposit. I wanted to use laid down because we do use that terminology a lot when we're out in the field. I just want you to be aware that that also means deposited. Rock formations are laid down horizontally and continuously. Meaning, I don't mean all the time, I mean in a continuous layer. The layer itself doesn't get interrupted. What's up?
So I can't really read your hand. Original on 3. What's it say?
Horizontality. You can listen to me though. Right, you can hear what I'm saying. And then also within cross-cutting features, we should probably include inclusions. It's the same kind of deal. The chocolate chips had to exist before the chocolate chip cookie could have chocolate chips in it. If there's a rock made of other little bits of rock, those little bits of rock had to exist first. That's called inclusions. And I'm going to erase that and write it again so that it fits in the box. Inclusions. So you could say that there are 3, like I have listed here. You could say that there are 5 if you separate out cross-cutting features and inclusions and original horizontality and lateral continuity. And you could also include these 2 together and have there be 4. But there's not really a set number seen as principles. It's not like the 4 fundamental forces of the universe that there have to be 4 of. These are just the easy way to remember them. And all of these things tell us what about rock? How relatively old they are. How old they are compared to other rock. And we use them to tell us about how old they are compared to other rock. On your test there will be, you'll get I'm just going to draw it over here and then we'll erase it and do the absolute one. You'll get a sequence, I don't know, like this. So let's, I have this sequence here. Let's say this one's sandstone. It doesn't really matter what kind of rock they are. But let's say that one's sandstone, this one's shale, this one's sandstone also. This one we could say is limestone. You remember these little symbols, right? That's one of the reasons I put this up. You remember the symbols for different kinds of rock? We'll say this one is granite. We'll say this one is granite. And we'll say this one is some kind of metamorphosed, I don't know, gneiss or something. Doesn't really matter. Okay, so using our principles, let's label these. Which thing had to be here? What thing had to be here first? Oh, this one has to, sorry, I made a trick question by making it unable to be answered. What should we make this be? I don't know, it's just gonna be filled in black. That'll be nice, there we go. Okay, what had to be here first? Yeah, this bottom layer here, which is this whole thing. This whole thing had to be there first. What had to be there second? The next layer above it. I'm just going to kind of fill it in blue. Now, what's next? Keep going.
The next layer.
Which is, what kind of rock is that? Actually, no, not the next layer above it. That's not right. What had to happen next? And how do you know?
The thingy right there.
Not this thingy, but this. The fault happened next. Because the fault goes across A and B, but it doesn't go up into the limestone. Okay? So then what was next? Then the limestone. I'll kind of fill that in orange. Then
And then that.
that dike. Yeah, and it's kind of hard to place this dike because the dike could have happened, since it only goes up into D, it could have happened after this had been laid down. We really don't know, but we might as well call it E. And there would be other ways. This is one of the instances where we use absolute age dating to tell us, was it in between D and the sandstone, or was it during D's deposition or whatever? Okay, so we'll call it E for now, and then we'll use this color green to be what's next.
The layer above.
Yep, sandstone, this sandstone here. Then what happened? I tried to draw these at an angle, but not these two. So you see, so then next was this uplift that caused these ones to no longer be originally horizontal. So the uplift would be G. Then this shale layer, H. Then this sandstone layer, I. Then what? And what's last on here? The valley, J. Because it cuts across these other ones that must have already existed. It's kind of like a logic puzzle. You just go through it and figure out, like you start with superposition and then use the other rules as they apply. Do you have questions about how that would be done? It's pretty fast, but do you have specific questions? Do you think you could do something like that on the test? Usually it's matching. The one on your test would be matching. It'll say like, you wouldn't have to like write that G is the uplift. It would say uplift of layers, whatever, and they'll be lettered, and then you'll have to match which one came first. You think you do that? Anyone else? Or questions about it? Okay. Hearing none. Do you intend to draw this? You're not required to, but are you currently drawing it? I won't erase it if you are drawing it. Okay, I'm going to erase Steno's principles then. Is anyone still using Steno's principles? Okay. Those are by far Steno's principles, the relative age dating, are the ones we use the most because, as we're going to talk about right now, absolute age dating, I'm going to cross this out and write absolute up here. Absolute is something we would have to do in a laboratory, and we don't really usually have access to it. So what is absolute age dating then? If relative was comparing rocks to one another, what would the absolute age dating be? Remember, Tristan's height being 1.8 meters was absolute. It's numerical. So how would we do that with rocks? What can we tell about a rock that might give us its age?
Well, some rocks, like some sedimentary rocks, have fossils in them.
Okay, yep, definitely. So the two main ways are fossils and radiometric. And the fossils one, we know about what are called index fossils sometimes. Index fossils are things that meet these criteria. They have to have been widespread. We sometimes say the word cosmopolitan, which in addition to being your favorite magazine is also a word that means over the whole world. It's related to the Greek word cosmos, which means everything, meaning that the organism existed not just in a tiny little spot, because if it existed in a tiny little spot, it's not useful for everyone. So it has to be widespread, had to have been short-lived. And people are confused about this one, but really it's nice if it's short-lived, because if it only existed for 10 million years or whatever, we know if we find one that it was in that 10 million years. So widespread, short-lived, easily identified. It doesn't really work if it's a clam and we can't tell it apart from other clams. The other two don't really matter how widespread or short-lived it was. But these things help us to understand, like for instance, if we find, in layer F here, we find an Inoceremus fossil, which is a very commonly used index fossil. The Inoceremus is Cretaceous in age. And so that tells us, if we find it, that this layer, well, first of all, it doesn't tell us just the age. What else does it tell us? If there's a marine clam called Inoceremus in layer F, what does it tell us about layer F?
That it was around during the whatever time.
Cretaceous, but it's also an ocean, because that's what a marine clam lives in the ocean. So we can learn a lot about a layer of rock by the fossils that are in it. And then as far as radiometric, we use radiometric dating. What we do is we compare parent to daughter isotopes in the rock. Yes, Carly?
Do you have big notebooks?
Like notebook paper?
Like
No, I'm sorry. If I did, I would give them to you. So I'm trying to think of a specific example. Zirconium's commonly used. I don't know the half-life of this zirconium isotope, but we find a certain isotope that we know decays into another one, and we measure the ratio of those two. For instance, uranium, I'm not even going to say the isotope's number because I'll probably get it wrong, but some kind of isotope of uranium and the lead that it eventually decays to, and the half-life of that, I don't know, I'm just making it up, but we'll say it's 250 million years. So that means that after half of it has decayed, as you remember from physical science, 250 million years must have passed. And so if we go to the rock and we see, oh, there's half lead and half uranium, this rock is 250 million years old. If it's 75% uranium and 25% lead, it's half of that, it's 125 million years old. So we use the half-lives of the radioactive isotopes and how much is left within the rock to tell us how old the rock is. This is like carbon dating. You've heard of carbon dating? But that's absolutely useless in paleontology. It's useful in archaeology. What's archaeology?
Artifacts.
Yeah, of human artifacts. Paleontology is a study of ancient life. Archaeology is a study of ancient humans, which that has a whole different meaning of ancient. It is useful for that because the maximum range for a good carbon date is about 50,000 years. Fossils have to be more than 10,000 years old to be even considered fossils. But that's obviously there's a little bit of wiggle room there where maybe we can use carbon dating for something and maybe we can't. But for most fossils that we find, carbon dating is off the board because it's just not feasible. Doesn't last that long. Would you like to talk about fossils next, or do you want to talk about geologic time next? Because we can go either direction for this.
A few minutes to catch up, be all caught up.
Okay.
Because I'm still on the drawing. Yeah, me too.
You have done the explorations, is that correct? Let me make sure I assigned it, and if I didn't, I will do it now.
Well, we obviously did it last
I don't think we did this unit last year, so I don't think so.
year.
Yes, I assigned it on the 16th. It is due yesterday. 5 people not started. The only person who started was Marissa Conraff, but you didn't finish, you say. Let me change this so the date is tomorrow like it's supposed to be. Probably only have time to talk about stuff on test 1. Yeah, let's just talk about geologic time and fossilization, and then we'll be through with these notes. But that just covered test 1. But would you rather take test 1 and then do the notes for test 2 and take test 2, and then do notes for test 3 and take test 3, or would you rather do notes 1, 2, 3 and test 1, 2, 3 all at the same time? Because we've done it both ways. Which do you prefer? Okay, since that's the only opinion I've heard, then that's what we will do. And you'll all be here tomorrow. So tomorrow we'll do the notes for 2, and I will assign lesson 2.
Just to be sure, that is the absolute side.
Yeah, I changed it to absolute because I wanted to keep this up because people were still using it. Do you know what these two words mean? This was from physical science, but some of you didn't take physical science here, and some of you, it was a while ago. What parent isotope and daughter isotope mean? These are referring to radioactive isotopes, and the parent isotope becomes the daughter isotope. So for instance, let me look up an actual example that is used in geology, and I have my laptop right here, so I might as well do it. We're going to look at the isotope of uranium that is commonly used. That'll give us a more specific. If the internet would not choose this time to be annoying to me, that would be much better. Let's use the uranium one that I was talking about before, if it would ever load. Okay, so uranium-238 in a chain, it doesn't just happen directly from uranium-238 to lead, but in the, I'm going to erase this down here, and I'll erase this line too, and we'll give an example of this radiometric thing. So uranium-238, also expressed like this, but we say both of them as uranium-238, becomes lead-206. So both of these are pronounced uranium-238 becomes lead-206. And this process takes, it says, 4.47 billion years. So 4.47 gigaannum equals the half-life. That little symbol there, this little guy, that's the Greek letter lambda. That means half-life. So what we do is we look into the rock. We use usually either X-ray or visible light diffractometry, which is where we cut a thin section of the rock, zoop, put it under the diffractometry microscope, which uses polarized light, and we can tell, oh, this crystal contains the uranium-238, this one contains lead-208. This may not be true for this particular one, but it is true for the zircon one. And we can see, if they're roughly half, we know that rock is this many years old. That rock has existed this long. If they're roughly half, because 50-50, that's one half-life has occurred. Usually they're not that old, and so maybe it's 75% uranium-238, 25% lead-206, and that means one half of a half-life has occurred. Meaning the rock would be, what's half of 4.47? We'll say 4.5. What's half of 4.5 gigaannum? 2.25 gigaannum. So it'd have to be 2.25 gigaannum old. That's the way we do radiometric. And this one's the parent, because it becomes, this one's the daughter. Yeah? Good on absolute age dating?
I feel like we did that in chemistry.
We did. Yep, we talk about this in chemistry too, and physical science. So we use a combination of radiometric absolute age dating, fossil absolute age dating, and relative age dating to tell. Because for instance, this crystal here that I have colored in black, this might be an excellent source of zircon or uranium or something that has a definite half-life. And so we can say this, we analyze it and we say this has an age of 2.25 gigaannum, as I say. So this one is 2.25 gigaannum. We know that everything else must be, or everything above that must be older than it. I'm sorry, younger than it. We know that everything it cuts across must be older than it. And so we get a lot of information. If we just date one of these things, we get an awful lot of information about the way things are. Let's talk about geologic time next. We're going to, what divides geologic time? Like, what are the things that stop the, let's call these, we have eons. In geology, it's customary to organize them from the oldest on the bottom to the newest on top. And that's, you can see why, because of superposition. So we have the Hadean eon, followed by the Archean eon, followed by the Proterozoic eon, followed by the Phanerozoic eon. The one we're in right now is called the Phanerozoic. These are all eons. And then those eons are divided into eras. Let's just do this one. So these ones are going to be the eras of the Phanerozoic eon. We have the Paleozoic. I'm trying to figure out the best way to draw this. Paleozoic, Mesozoic. This is probably not the best way to draw it. And the Cenozoic are all, like, do you understand my little diagram here that I've tried to, like, these are all shoved into the Phanerozoic. Like, the Paleozoic doesn't go down here. Does that kind of make sense? Like, this little, I'm trying to represent that it goes in to the Phanerozoic. And then each of these is divided up into, did I say eras for this one? Let me look at it. Do you still have your geologic time scale? Have I not handed one out this year? Oh, I'll do that in a second.
I got the whole song.
Good. Yeah, these are eras. Is that what I had said earlier? I'm sorry. These are eras. And then those are divided up into periods. For instance, Kyla's question that she answered correctly at Quiz Bowl that I was very proud of her for, the periods of the Mesozoic era are the Triassic, Jurassic, and Cretaceous. And these are...
Cretaceous is what they're in. On Dinosaur Train, always go for Cretaceous.
And these are periods. So eons, all of these eons are divided up into eras. The ones you need to know are these. So you have to memorize all the eons in order. What's the oldest?
What does the second one say? The
Archean. Let me rewrite it for you. Archean. So Hadean means like hell. Archean means ancient. Proterozoic, the root word there is zoos, life. So this is kind of like proto-life, like the first vestiges of life. And then Phanerozoic means full life, like life has taken its full form. And that hints at what we use to divide these things up. You need to know the eras. You have to memorize the eons in order, the eras of the Phanerozoic, only the ones in the Phanerozoic in order. What's the oldest era in the Phanerozoic? Paleozoic, then Mesozoic, then Cenozoic. Once again, the root word is zoos. Paleo means ancient, Meso means middle, and Ceno means recent. And then you have to have memorized the periods of only the Mesozoic era. Triassic, Jurassic, Cretaceous. That's what I ask you to memorize. And then, just so you know, each of them is further broken up into epochs, but you don't have to know what those are. That's the geologic timescale. What divides these? Like, what divides, usually, it's not always true, but what events divide that? We just cut it off right at...
Well, it's usually like life, not like life-changing, but like
Yeah.
evolving.
Yeah, total life-changing. Like, you don't just mean life-changing like in your life. If you won $1 million, that would be life-changing. You mean like life in general, zoos, the entirety of life, on planet Earth has changed. Yeah, it's usually an extinction event, or in some cases a mass diversification, like all kinds of life explode, as in the Cambrian explosion. You'll get into more depth in this in your explorations. We're running out of time. We were going to talk also about fossil preservation. We'll do that when we do our field trip, or maybe before it. Fossils can be preserved in a number of ways. We'll just kind of leave it at that. There are quite a few that you need to know how they're preserved, but there are things that we talked about before when you were in 8th grade science, things like cast and mold, permineralization, petrification, things like that. But fossils, I'll just draw a picture of a fossil to go here. That'll be nice. Look at him. Nice. So relative and absolute age dating, the geologic timescale, and then we'll talk more about fossils. Do you have questions about any of this? Do you have notes over all of this? Bye. You still have, I said bye. Please stop when I tell you to stop. Is teacup in the way? Get out of the way, teacup. Maybe it's not close enough.